So I called this various two-dimensional force problems. By two-dimensional, hey, stuff at angles. You're probably going to mean components. Okay. The first one is the classic lawnmower problem. I like this question. I like this question. I like this question. What do I mean by a lawnmower problem? Where the ground is flat, but the applied force is at an angle, as opposed to the ramps that we've been doing. And we're going to solve it very similarly, but we're going to break the angled applied force into components. And once again, race, the normal force ain't going to be no mg, which is really going to be the key to this. So what's the lawnmower? By the way, we call it the lawnmower problem because when you're pushing a lawnmower, which way does the lawnmower travel? Can you stop doing that, please? Which way does the lawnmower travel when you push a lawnmower? Horizontally. But do you apply the force horizontally? Really and truly stop doing that? You apply the force diagonally down the handle at an angle. Yes? So, a problem where we have vertical force components other than the normal force and mg. And here is the key. Normal force won't be mg. Or on a ramp, normal force won't be mg cos. What'll it be? Oh, it'll be, look. I know more than one force the same size as the normal force, and I'll have to think about it. As an example. Example 1 says, find normal force, friction, and acceleration. I'll be honest, if I give this to you, I'll just say, find the acceleration. And I'll expect that you clue in that to find the acceleration, you'll have to walk through these steps. You know what? Let's call this part A, part B, and part C. What am I going to do first?
Break it into components.
Before that, he said break it into components before. Okay, I'm going to label my forces. I could draw a free body diagram. Since they gave me a lovely picture, I'll label the forces here. Hey, what are the forces acting on this 50? Get the obvious one. Darn right. What else? Normal force. I'm going to come back to that. Yes, and that's important. I'm going to come back to that because it's going to be weird. What else? Friction. Which way is this thing moving, do you think? Which way is this thing accelerating? To the right? So which way do you think friction is? To the left? And then, Michael, what did you say? Okay, I've got the applied right here. Cliff, what was the first thing that you said?
Component.
He thought, I knew I had faith in him. He said, you know what? I know we haven't done the normal force yet. Let's break this applied into components. Now, since it's pointing down, it's going to be that and that. Yes? You know what? Here, I think we can call it Fy and Fx. We can use vertical and horizontal because Neve, we are vertical and horizontal with the ground. We're not on slant. Can you see why I delayed drawing the normal force? I don't know the normal force. Oh, but look. I know two forces the same size as the normal force. What does the normal force have to cancel out? Mg and Fy. So is the normal force going to be bigger than mg, smaller than mg, or the same size as mg? It's going to be considerably bigger. In fact, you know what? It's going to be exactly that big plus that big. Why don't I eyeball it a little better than that, Mr. Dueck? It's going to be about that big. By the way, friction is what times what? Mu times a normal force. By pushing in this way, will friction be bigger or smaller? Bigger. So this is a stupid way to try and move an object. Now, why do we have lawnmowers designed that way? Because lawnmowers have what? Wheels. Friction is not a big issue. Not a big issue. There's some, but it's near zero. So who cares? But certainly sliding something that way would be stupid. Why is this so hard? Because you're increasing friction, because you're increasing the normal force. In fact, if you've ever moved something really heavy, you don't just slide it. What do you do at the same time? Lift! Why? Did that change the mass? No. It changed friction. How? Because it lowered which force? Normal force. Of course. Okay. So A says find the normal force. Do you agree with me? The normal force is going to be equal to gravity plus Fy. But we can do more than that, I think. Let's see here. Here's my 20-degree angle. So Fy, opposite, adjacent, or hypotenuse? Opposite. And this 200 here, adjacent or hypotenuse? Mr. Dueck, are we back to y is sine? I think in this case it might be, although I'm not sure it'll be that way always, so I'll be a little careful. But I think I would say this. The sine of 20 equals opposite over hypotenuse. So yeah, I guess if I walk over here, this is going to be mg plus 200 sine 20. Which is what? Who's in calculus? Make sure you're in degrees now. Have you guys done any trig yet? Okay, I take that. I was helping some people a little bit. I did I did the sine of 1 over x to the x or whatever, one of those funky limit graphs. But that one only works if you're in radians. 50 times 9.8 plus 200 sine 20. The normal force is 558 newtons. 558.4, well, 3 sig figs, and I'll keep the extra answer in my calculator. Kelly, what's B asking me to find? Friction is what times what? Friction is what times what? Mu. Thank you. Right? I don't know the... Oh, wait a minute. I was going to say I don't know the normal force. I just figured it out. I do know the normal force. Holy smokes. Kelly, what's mu? I don't know. What's mu with you? No. Kelly, what's mu? It's in the question. It's in the diagram. Look. What's mu? Yeah, you with me? Hey, what was the normal force? 558 point something. No calculator. What's 0.1 times 558? 55.8. That's friction. Ashley, what's C asking me to find? Who's winning? Okay, now, ready? We got to think very carefully. Look at my free body diagram. Look at my diagram. Which way did you tell me this thing was accelerating? To the right? Who's winning? Don't you dare say 200, because that 200 is slanty and I can't use it. Fx. The component of that 200. Who's losing? So my equation now is going to look like this. Hey, if Fy was sine, what do you think Fx is? Let's just convince ourselves oh yeah, you know what? It is adjacent over hypotenuse, yes? Okay, so this is going to be F cos theta. I'm going to get this. 200 cos 20 minus 55.8 equals, oh, Ashley, how would I get the A by itself? Yeah, and so can I divide by 50? Is that okay? It's going to be bracket 200 cos 20 minus, oh, you know what? I'm going to go 0.1 times my answer button because that's how I would have calculated friction, and that way I'm not rounding off at all. Woohoo! Divided by 50, do you get 2.64? No, yes? Yeah. So for the lawnmower question, Callum, there's two possible scenarios. I'm either pushing down at an angle, which makes the normal force bigger, or I'm lifting up at an angle, which makes the normal force smaller. In fact, the question will be identical, except I think you'll find that the normal force equals gravity minus Fy. Okay. Hey, what happens if Fy is the same size as gravity and you're lifting up and there's a minus sign there? You've just lifted something off the ground. You're exerting such a big vertical diagonal force, and it is possible to pull an angle and still lift something off the ground. Absolutely. You just applied a big enough vertical component to be bigger than normal force, to be bigger than mg. So the lawnmower problem. Example 2 says, write force equations for a mass on the ramp as shown below. The system is at rest. Okay. What are the forces acting on this block? Get the obvious ones. Gravity. Yoink. By the way, I think I said this before, but I'll say it again. You've clued in that when you're using this method, when you drop gravity down, you always put the mg on the same side as the pointy angle, because then it's not in your triangle and less confusing. Yes? What else? Is there friction? Does the question say frictionless, or there's a mu? Okay. There's a friction. There is a normal force. That, again, is going to be a weird one. I'm going to save that one for last this time. Which way does this ramp want to slide? Sorry, which way does this block want to slide? Down the ramp? So which way is friction? Okay. I also have this F applied pushing down. Now, I can break gravity up into mg perpendicular and mg parallel. Which force did I forget, Sally? Which one did you want me to add? I think you said it. Normal. Okay, normal force. Now, look. Is the normal force going to be bigger, smaller, or the same size as mg perpendicular? Why? Because it has to cancel this out, and it's got to cancel this out. So this is going to give me a normal force, something like this. In fact, if we were talking equations, I would say the normal force equals the applied plus perpendicular. And friction is mu times the normal force. Oh, and then the fact that it says it's at rest means it's a tie. Gravity down is canceled out by friction up. Where friction is mu times the normal force. I don't know the... Wait a minute. I do know the normal force. It's F applied plus mg perpendicular. What's mg perpendicular? Of course it is. Right? Really? That good? Okay. By the way, did it say solve? No, it just said write the force equations. Those are the two big ones. I got my perpendicular force equations and my parallel force equations. What are you pointing at there? Oh, okay. Over on the shelf back there. The good ones with the lotion. I spend money for you guys. The second one. The static equilibrium problem. What's the definition of a static equilibrium problem? An object that is at rest. If it's at rest, what's its acceleration? Sorry? 0. Oh, if its acceleration is 0, what's its net force? 0. Okay? So an object at rest has 0 acceleration, and therefore all the forces are balanced. Its net force is 0. You're really having trouble holding on to that pen. I'm really and truly going to say, stop dropping it, because it's loud. Elijah, can you read example 5 to me? You better believe there's tension. Sorry, can you read example 5 to me? Okay. This is not on your test. We're going to do a whole unit on this, and I'm probably going to do it as the very last unit of the year. It's the unit on equilibrium. It's the unit that I save in case we have like several snow days. If there's one unit that I don't cover in Physics 12, it doesn't overlap with anything else. But if any of you are going into physics or engineering next year, I'll put the lessons online as videos. You'll have homework over the summer. Sorry. Although last year I did get through that whole unit. 2 years ago when we had the 3-day strike, I did not. So this is not on your test, but I always plant the seed. It says find the tension in both cables. What we want to do is we're going to do a free body diagram. Well, we're going to label the forces. We're not going to label the forces on the mass, because the only force on the mass is mg. We're going to label the forces on the spot where the ropes connect. What are the forces acting right there? Get the obvious one. Really? Get the obvious one. What else? 2 cables, 2 tensions. Tension 1. Tension 2. Now, I could do this all with components. I could break that cable 1 slanty into vertical and horizontal. You know what? There's a better way. Because I know that the net force is what? 0. How many forces are there, Peter? Peter, how many forces are there? Tension 1, tension 2, and mg. How many forces are there? Put pencils down. I'm going to add these 3 vectors together. How do I add vectors together? Why, I draw them tip to tail. How am I going to add 3? I'm going to draw them tip to tail and then draw them tip to tail. Okay? And there's a trick to drawing these. You always draw the easiest one first. Of the 3 forces, which is the easiest or obvious force? There's one more reason why I teach this method. What's the easiest force? Draw that first. Watch. Don't write this down. You're going to draw it yourself in a second. Looks like that. Then you always draw the ugliest force next. Of the 2 remaining, which one's the ugliest? Tension. Now, tell me when to stop. Why do I have to stop there? Because but you saw I added those 2 together, tip to tail, yes? Because when I add the 3rd force, tip to tail, I know what it looks like. It's exactly what? Horizontal. See it? That's why I saved it for last. I want the 2nd easiest force for last. First, easiest, because I need to know how to start. Ugliest, because I'll be able to figure out where to stop, because I know my 3rd one. By the way, did I end up back where I started from? Yeah, what does that mean? What's my overall force? If that was a displacement and you ended up back where you started from, what was your displacement? 0. It's a force, and I ended up back where I started from. What's my net force?
0.
That's a picture of 0. But do you notice? It's lovely SOHCAHTOA trig. What can I fill in? That's mg. Yes? That's tension 1. Yes? That's tension 2. And where does that 35 degree go? Top right or bottom left? See it, Neve? How am I going to find both tensions? Because I know mg. I know the mass. Tension 2, opposite, adjacent, or hypotenuse? Tension 2, opposite adjacent or hypotenuse? Opposite. Tension 1, hypotenuse, mg, adjacent. Curtis, what do you want to find first? Oh, yeah, let's find tension 1 first. So I'm going to find tension 1 using mg. Which trig function? Ah, is right. Which trig function? Cos. So for tension 1, it's going to be cosine of 35 equals what over what, Curtis? How would I get tension 1 by itself? Oh, stuff moves. Hey, we're back to holy smokes, like day 2 of physics 12. Do I have 1 fraction equals 1 fraction? I do if I imagine that the cosine is over 1. Stuff moves how? Diagonally. Remember that? So tension 1 is mg over cos. What was m? 10? Okay. Oh, 10 times 9.8 divided by cos 35. I can do that. Do you get 120? 119.6, go to 3 sig fig. 120? Yeah? Okay. Let's find tension 2. Hakeem, which trig function can I use to find tension 2? I could use sine, but let's not, just in case we got tension 1 wrong, let's try and use mg. Which trig function? Tangent. Tan 35. Hakeem equals what over what? What does tension 2 equal? Oh, mg times, yes? 10 times 9.8, tan 35. 68.6 newtons. That's how they're sharing the load. That's how they're sharing the load. That's equilibrium. That's a 3-chord equilibrium question. You can do them with components, but I'm telling you, it's way easier to add them tip to tail to tip to tail to tip to tail, and they'll end up back where you started from, and you know they have to do that because your net force is 0. Draw the easiest force first, the ugliest force next, the next easiest force last. You'll always be able to figure out how it goes. And then it'll either be SOHCAHTOA or it'll be sine law if it's not a right angle. What I've just showed you is way faster than trying to do this by breaking everything into components. It can be done. It's a lot of work. Oh, example 6 says draw the vector addition. We already did all that. Number 3. Accelerometer problem. What's the definition? A non-equilibrium situation which only exists because the system is accelerating. Your net force isn't 0, but an object that's accelerating tends to move in the opposite direction to the acceleration due to its inertia. I've talked about this in physics 11 and race. I think I talked about this in physics 12. I said our bodies have built-in accelerometers, Neve, but they're backwards. Have I done this speech with you guys before? Yeah, I did it in physics 11. Okay, Bree, because put your pencils down. So Bree, I convinced you we have built-in accelerometers, but they are backwards. Okay, but that's, by the way, if you're ever on an amusement park ride and you're wondering which way am I accelerating, which way do you feel? It's the opposite. I'm telling you, it is always. Okay, so let's suppose this rail car is accelerating, and because there's a mass hanging from a string, and as such, it's keeping the pendulum at that angle. Now, as soon as it stops accelerating, as soon as it hits a constant speed, that mass is going to come swinging down and hang normal. But I'll show you. Hello, where's my little toy? Here it is. I'll simulate the same thing here. You'll have to watch really close. So here's the mass hanging from the string. I'm going to accelerate to your right. And if I do that, hopefully you'll see the string does pick up an angle. Ready? Was it for a split second there? Right? It hung like that for a split second. Imagine if I was on some kind of a car and could keep accelerating, keep accelerating, keep accelerating. It could hang like that for a while. Of course, as soon as I stopped accelerating, it swung back down. That's what we're talking about here. Find the acceleration. Okay. Well, what are the forces acting on this here string? Get the this mass. Get the obvious one.
Gravity.
What else? Ah, no. Relax. How many forces are there? This is meant to be really obvious. How many forces are there? Let's add them together, tip to tail. I'm going to do that by, because I got weird. I could go components, but I'm going to bring a little vector math. By the way, this also won't be on your test. That's why I said last day we technically finished the unit lesson 7. How would I add these together, tip to tail? Draw the easiest one first. What's the easiest one? Then it looks like tension goes up to the right at an angle. Now, which way, what direction is this car accelerating? Exactly horizontally. What direction is my net force? Exactly. What direction is this car accelerating? Exactly horizontally. What direction is my net force, therefore? Exactly horizontally. Which means, tell me when to stop drawing tension. Tell me when to stop drawing tension. Right there. Why? Because I know that when I add those two together, there's my net force. By the way, what angle is that right there? Sorry, look up. What angle is that right there? 32 degrees. What angle is that right next to it? 90 minus 32. What angle is this down here? 32 degrees. This angle and this, you know what? This angle right here is. Can you write an equation relating F net and mg? Which trig function? Which trig function? Yes? Wait a minute. What is the equation for F net? What has F net been since physics 11? 2 letters. This is really just right? Neve, did they tell me the mass that was hanging? Why not? Oh, ha! Look at that. In fact, Neve, what did this question want me to find? How would I get the A by itself? I totally agree. A is G tan 32. You get 6.1, 2? Yeah? What if, instead of having it hang at an angle, what if you wanted a 90-degree angle, so it was hanging straight down? What if you put a 90 right there? Can you go 9.8 times the tangent of 90? What happens? You got a math error. Here's what it's saying. you can't possibly have an acceleration and an angle of 90, because as soon as you have an acceleration, it has to move. It's saying, I'm sorry, there's no way you can be hanging straight down and be accelerating at the same time. It's impossible.
What about if you're accelerating up?
That's not what this question, that's not how I set up this question. The reason F net is horizontal is because I said so yeah, if we're accelerating up, totally different situation, but a totally different triangle, and I'll bet you a different trig function. I'll bet you. What if you wanted to, could you ever get it vertical? Could you ever get an angle of 0 degrees? What's 9.8 times tan 0? What is the tangent of 0? 0? Yeah, you know what that's saying? Because it's not saying that if you're stopped, it's going to be horizontal so that the angle is not. It's saying you can't do that either, unfortunately. So let me be Claire, will that be on your test? No. A couple of units from now? Yeah. Well, at the end of the year. I'm planting the seed. And this is good forces review. Example 8, if a race car, or if a rail car is lowered down a ramp at a constant speed, that's probably important. Which diagram shows the correct position of a hanging pendulum, of a hanging mass? A, B, C, or D? What do you think? Oh, people are doing some deep thinking. Who says A? Who says B? Ah. You'd be correct. Convince me. I'm not going to, this one, we could do algebraically. It's kind of pretty. I want to cut things short and give you lots of time to work on a take-home quiz. But think about this right here. First of all, constant speed means your acceleration is what?
0.
Which is just the same as stopped, because that's also a constant speed with an acceleration of 0. So here's my hand. There, now it's on a hill. You saw me tilt my hand? Did the rope's angle change with the ground at all? Oh, I'll put it on an uphill. No? No? I'll put it vertical. No? Okay. Yeah, B. It's going to continue to hang straight down. Why? Constant speed. And the way I'd probably tackle that one is constant speed really is the same as stop. It's not, but in terms of physics, we've said you can't tell if you're moving or not. If you're moving at a constant speed, you have no way of knowing. So that's probably how I'd answer it. So explanation, meh. I'm going to skip example 9. What's your homework? Take-home quiz, except I do want to give you a couple of lawnmower questions because I like the lawnmower, I like the lawnmower, I like the lawnmower, I like the lawnmower. So, number 1. Number 2. Nah, 3, no, that's overkill. Meh, 4, no, that's overkill. Meh, meh, meh. Eh. Yeah. Ah. I can even see I added this question because this is from an old provincial exam. I can tell by the font and the graphics. I like that question. I like that question. I like that question. $12. 13 and 14. Okay. I must have added those this summer. I'm glad I did. Hey folks, that's forces. The rest of your homework, you can start whittling away on the, so take-home quiz for sure Friday. Friday, I'm pressing pause. We're going to mark the take-home quiz, no new homework, and you can start whittling away at the great big uber huge vector dynamics review.